Hello everyone, good morning. My name is Vipin Sharma. I'm working as the engineering lead for the backend for Watson Orders. Watson Orders is a voice AI based automated order taking solution. It's especially designed for drive-throughs and it's basically Siri or Alexa designed for taking your orders. So we work in collaboration with McDonald's. Burger Hack is the name of their hackathon that happens every 2 years, I believe. So that's where that statement is coming from, that I love burgers to burger hack everything. And IBM McNugget is just like our kind of our collaboration. For collaboration, we call it like IBM plus McNuggets from McDonald's, so we call it IBM McNuggets. So with that, welcome to the talk. The topic of my talk is distributed systems. I'll be going over some of the common challenges and solutions that we can face it while we are building the distributed systems specifically for the edge and IoT. So with that, let me get started. So regarding the agenda of my talk, I have divided my talk in 3 parts. In first part, I'll be going over the overview of the distributed systems. We'll be going over the applications and their significance in today's software industry. In my second part, I'll be taking a case study. I'll be going over a problem regarding the traffic generation at hyperscale and how we solve it with the help of the distributed computing. In my last section, I'll be sharing some of the learnings that we learned while building distributed systems application. With that, let me get started with the first section. So let me start with the overview of the distributed systems. So distributed systems, what are they anyway? Distributed systems are a collection of compute units working in tandem with each other towards solving a common problem. That's essentially are the distributed systems. However, an interesting aspect of the distributed systems is the physical distance between the compute units matters. What does it mean is 2 compute units, even if they are working in tandem with each other and trying to solve the same problem, if they are on the same motherboard, or essentially if they are sharing the resources, like for example, the operating systems or the memory, then technically that's not a distributed computing. That's still a parallel computing, but it's like more of a multiprocessing or maybe multi-threading, but that's not distributed computing. For distributed computing, 2 compute units, they have to be physically separated. And what essentially that means is somewhere leveraging network, internet network, or basically computer networks to leverage to establish the communication with each other. With that, what is the significance of the distributed systems? I think. Maybe I'll just, So distributed systems, why are they important? Distributed systems are the backbone of software industry today. If we look at any major industry, like in software, as part of the software industry, it is somewhere established on the distributed system concepts. Let's take the cloud computing or edge computing or Internet of Things, cybersecurity, e-commerce, or even the ML and AI, like machine learning and AI systems. Like when we are doing the training of the models, we are technically doing the training on the cluster of GPUs, and that is somewhere achieved with the help of the distributed system principles. And these industries are large. For example, cloud computing, it is targeted to be a $600 billion industry by the end of 2024 itself. Having said that, it's not just the software industry basically which is leveraging these distributed systems. Even if we look at the day-to-day applications that we are using, if you pick up our desktop and like look at the applications that we are, almost every application that we are using these days, it somewhere is using the distributed computing principles. For example, if you take the Microsoft Office, Word, PPT, like Microsoft PowerPoint, all these applications have somewhere become like, while they used to be standalone desktop-based applications way back in 1990s, they are leveraging the distributed computing, and these days, like, they are connected to the servers, they are giving you the designer ideas, and all those things are being achieved with the help of the distributed computing somewhere. Similarly, all other applications, Slack, Outlook, even browsers, items, Zoom, WebEx, Visual Studio Code also, like the developer environments, also they are slowly shifting towards the distributed computing. For example, if we see the Visual Studio Code, It is when with the help of this GitHub Copilot integration, when it is automatically suggesting the coding styles and the suggestions on the code, that is somewhere happening with the help of the distributed systems. It is connected to the servers in the backend, and then those suggestions are coming. So all these applications also have become like distributed computing based. With that, yeah, I think let me go up and see if I can just. Yeah. So this is just my personal observation, like standalone desktop-based applications are shrinking at rapid pace, and if they are not extinct already. And this is like some of these features, for example, automatic updates that we are getting, over-the-air updates, sending the error reports back to the server, or all this data collection which is happening for the better personalization. That is somewhere like at the behind is using the distributed computing principles. With that, having said that, a truly reliable distributed system must support these features for it to be called a truly reliable distributed system. These features are fault tolerance, high availability, consistency, scalability, predictable performance when we scale the solutions, and security. Distributed systems are quite complex to build. That's because there are many integrated moving parts. When we have to design these truly reliable distributed systems, we have to look into the multiple aspects of the solution, which are, for example, the cluster management. We have to look into the resiliency of the systems. We have to work on the database integration. We have to work on the scalability aspect of the solutions. And to help it achieve all in tandem, we have to also have observability, which is the critical aspect of the distributed systems. With that brief overview, let me actually dive into a case study that I would like to share with you all. In my previous tenure at VMware, I was working for NSX, which is software-defined networking. It's basically a network virtualization tool based on the software-defined networking principles. It's a cybersecurity software also in a way that it offers the micro-segmentation features like micro-segmentation and distributed firewall, which allow customers to set the highly customizable security policies. This is deployed in the on-prem as well as cloud environments, and basically the scale of the deployment is like quite high. Like for example, there are easily 10,000 to 50,000 workloads where it is getting deployed. So as part of the development team for this tool, once I was basically assigned a task to build a tool to validate these features before they are released. So for validating these features, for example, the distributed firewall, when it has to be validated, we have to essentially check for the firewall policies to be applied correctly. However, the challenging part is we have to validate it at the scale. What does it mean is that typically there will be like 10,000 to 50,000 workloads. There will be almost 150,000 firewall rules which are being applied in the system, and then we have to test whether the firewall rules and those policies are working correctly or not. Besides, not only for the functionality part, but also for the durability part. For example, we would like to see that once I have applied a firewall rule for access, I would not want it to go away, let's say, in 2 days or 3 days. I would want to test it like it is working as expected over the period of, let's say, 7 days or even for the months. So validating these features is quite complex because of the scale. As we can see, on a simple test bed of 3,000 virtual machines and having maybe 8 to 9 network namespaces itself, it becomes like almost 500 million endpoints pairs. There are like 27,000 IP addresses, and that becomes like almost 500 million endpoint pairs over which we can test, apply application of the firewall rules and different kind of rules, and then basically testing them whether they are working correctly or not. So it becomes a quite challenging problem. And once we started digging into it, we wanted to first explore what are the existing solutions in the market, if we can leverage them. So we evaluated what are the existing traffic generation tools which are available in the market. So we explored a couple of these utilities which are available, for example, ping, fping, hping, iperf. However, we found that almost all of them have their one or the other limitation. For example, ping, it can ping only one endpoint at a time. Fping, which in a way offers a solution which allows you to ping to multiple endpoints at the same time. You can, for example, from the command line utility, you can mention multiple endpoints, but it is still over the ICMP protocol and not the TCP and UDP protocol that we would want to test for our firewall policies. Similarly, HPing was another utility which was allowing to test the TCP protocol, but it was not allowing to test the UDP protocols and other, even HTTP, etc. iPerf, NPing, Spirent, they had their own kind of limitations. Spirent, for example, was a paid tool. Having said that, our problem was even more complex in a way that some of these tools which existed in the market, they were not always supporting all the platforms that we wanted to test. When we have a solution like NSX, which is supporting not only the Unix and Linux, Windows, it also has to support the security and firewall policies at the ESX level, which is the hypervisor, from VMware, and it's it's the backbone of the infrastructure when we are building up the infrastructure, whether it is on-prem or hybrid or in the cloud environments. So those were some of the limitations of these tools, and we quickly realized we will have to build our own solution to test, to basically validate the firewall policies and these security features at the large scale. So with that, we came up with an architecture which was essentially leveraging the distributed system principles, and this is how the core architecture and flow of the solution look like. So we will be given a bunch of the nodes, there will be 3,000 to 5,000 VMs. We will be identifying as the very first step of the distributed computing, we will be trying to build a cluster of the nodes, and for that we will be identifying a primary node, and the rest of them will become the worker nodes. Then, as part of the agent preparation, or basically the cluster formation, primary node will be sending software package to the endpoints, all the endpoints like the workers over the SSH. It will be sending the configuration file as well, and it will be starting a Python-based service there, which will be a daemon service there. Once it comes up, those daemon services will automatically try to connect to the primary node, which will form the RPC channel. So in a way, in this environment, we have built the cluster of the nodes, like the cluster formation, and then we have established the RPC channel for the communication. Once that was established, we will be setting up the local databases also for persistence. For resiliency, we needed to have the persistence, the local state of the node we wanted to save in a certain way, so that when the node, if it fails and wants to come back, it will be able to come back with the help of the metadata which is saved in the local database on the node itself. Once this environment was set up, a typical request for traffic generation could be received on the primary node itself. For example, it will receive that, okay, I want to test, I have applied the firewall rule between two nodes, for example, let's say maybe two particular IP addresses, and I want that, okay, UDP traffic should be allowed, but the TCP traffic should not be allowed or should be disallowed. Once that kind of request comes on the primary node, it will identify where it needs to send those requests. It will identify those nodes where those IP addresses belong. We'll find out where we need to run the TCP or UDP client and on which node we need to run the server. Those client and servers will start doing the TCP or UDP or HTTP ping pong between each other. They will be saving the data, the results of this client and server ping pong on the local databases, as well as in a centralized database that we used Wavefront as a centralized database, as well as an observability platform. So this is a solution that we built based on the distributed system principles, and it worked quite well. Eventually, what we realized, the problem was very common even for the other use cases. For example, some other teams were doing something like threat scan, running the threat scan applications or the vulnerability scanning applications over this environment, and they wanted to do something similar. We wanted to control those applications from one endpoint, but at the end of the day, we wanted to start or stop packet capture or let's say some other open source, for example, Kali Linux based threat scanning or other basically security applications on those endpoints, and start and stop whenever it was required. So we realized that this framework that we developed eventually could be converted into a generic distributed application platform, and we could give more power to the developers. So we converted into a generic distributed applications platform released as an open source, which is available as a Python package as a Lydian. And the architecture is such that the common aspects of the distributed systems like the cluster formation, resiliency, RPC channel-based communication, and observability, and all those aspects are handled by the common framework itself, which is open source. And developers could write their own applications, whatever that application can be. For example, it could be the traffic generation, it could be the resource monitoring, simple resource monitoring at the endpoints, or it could be like packet capture, or you could build basically any of your application. So that's somewhere is the case that kind of ends the case study part. We built this as a solution like from the ground up. We used minimal external tools. We just built it on the bare metal and like the Linux and Unix itself. We didn't use Kubernetes or Dockers. We were using the native daemon services from the Linux and Unix, for example, systemctl and service. They were helping us in achieving the resiliency of the systems. So this worked quite well, but at the same time, while building this, we realized that made us learn some of the challenges that come up when we are trying to build the distributed systems, and that's what I would like to share in my last section of the talk, which is learnings. So let me dive into it. So the first learning that we had was like clock drift. Clock drift is a very common problem, but it's like one of the most critical one. When we have the distributed systems, we have at the large scale like 3,000, 5,000 VMs. The system clocks of individual nodes that over the period of time, it tends to drift. What does it mean is that it will become either slower or slightly faster than the other systems. And it causes a lot of challenges. For example, one of the common challenges that once the system clock has drifted, the timestamps of the logs on those particular nodes will start changing. It will be like not accurate. It makes the debugging issues much harder because in a way it's like, let's say primary node is sending a request to the remote host, but since the clock has drifted, we are seeing that we sent the request at, let's say, maybe 10 seconds, but then we are seeing, okay, request was received at 8 seconds or 7 seconds because the clock has drifted. So it poses a lot of debugging challenges in the traditional systems, like where, for example, if we take the case of the Cassandra or any other NoSQL database, which is based on, again, the distributed system principles, we can imagine like, the event ordering and database node synchronization and like transactional basically healing, transaction healing kind of problems. We'll see the problems if the clocks have drifted. In our case, the solution we took upon was like we set up a local NTP server in one of the nodes. What does it help is NTP is basically a network time protocol. We set it up we set up an NTP server on one of our nodes, and then we what we had realized, like in our case, the nodes were drifting. We're seeing the clock drift over a period of a day. So we set up a cron kind of a cron job kind of a thing that all the nodes will be synchronizing their clock with respect to this NTP server, and that helped us solve the problem. Having said that, NTP protocol is known to have accuracy only in milliseconds, and for the really large systems or where accuracy is supreme, for example, in the financial transaction systems, I can imagine like we would want to have accuracy in the nanoseconds, and that can be achieved with the help of another protocol, precision time protocol, that can be considered for solving the problem. Another problem that we faced, especially coming from the traditional system programming, was the network failures. Network failures are real. What does it exactly mean is that a request for operation or remote host has only limited rate of success to reach. What would happen is, let's say if I send a request to restart all of these 3,000 VMs from my primary node, or basically the leader node, almost always out of 3,000, maybe 2,800 nodes will receive that request, but 200 nodes will not receive the request. And that happens because of the network failures. There are these failures can be both types. They can be hardware failure, they can be software failure. In terms of hardware failures, they can be because of the switches and routers, they have the glitches. So it is only natural that when we send the request, it might not receive all the time. The solution in a way, to solve this problem, it's more of a paradigm shift in the programming style itself that we have to adopt. And one of the, we can take advantage of the SYNAC approach that is used by TCP/IP, which is highly successful. It's mainly successful because it has in a way, the concept of fault tolerance imbibed in its principles. So we used somewhere similar approach, like whenever we send a request to the remote host, we will not always assume that it will always be received, but we will be checking for the acknowledgement of that, okay, that the request was received. And also we minimized the requests over the network. For example, we started using the templates that helped us, instead of sending the 10 requests over the network to the endpoints, we started putting kind of the shell script or like, on the remote host itself, and just one request to run that command. Another lesson is like built for resiliency. Failures are inevitable. Even if the request reach on the remote host, there are only certain percentage of chances that that operation particularly will finish on that remote endpoint. For example, when I'm trying to restart all the 3,000 VMs at the same time, the hypervisors and infrastructure have their own kind of limitations, and some of the VMs will, even if they receive the request to restart, they will fail to restart. Those situations will arrive. To handle these errors, I think the only way to handle them is like we have to design the system with assumption to fail, that we have to consider the failure as part of the process. And we implemented the limited retry mechanism before calling it a failure. For example, if I send a request to restart all the 3,000 virtual machines, maybe 2,800 got started, maybe 200, even if they got the request, they didn't restart, but then we will do the retry mechanism for restarting them. So that helped. And then there are the concepts, for example, like load balancing that can be used to avoid the single point of failure. There has to be consensus algorithms such as RAF to be implemented when for example, the primary node itself also has as much chances of failure as any worker nodes. So to help recover from them, we had some of those algorithms implemented. Some of these challenges that we have discussed here, they are in general, like they're part of the distributed computing itself. Having said that, edge computing is nothing but kind of an extension of the distributed computing. In a way, edge computing is like enterprise computing brought closer to the sources where the data is being generated. And in case of the edge computing, there are some special considerations that need to be taken. For example, these are some considerations that I have shared that we have to consider when we are implementing a solution at edge. For example, application footprint matters. The memory and compute is limited at edge where the data is getting generated. So the solution for that is like we have to build lightweight applications with low memory and compute footprint. Power consumption matters, so we have to pick our protocols wisely. Some of the protocols which are very effective in regular scenarios, they are not as effective on the edge. For example, if I have to implement messaging platform, I might not prefer Kafka there. I'll rather use something like MQTT protocol, which is considered like low power. Network connectivity is highly unreliable, and bandwidth is very low. Although that is changing with 5G coming and like compute power becoming a little bit more stronger and growing at the edge itself. For that, one of the way to alleviate that problem is like keep dependency on network to a minimum where it can be afforded. And one of the most crucial aspect of the edge computing is like the security. Security is very crucial because as we take the edge computing to the data sources, like to the edge nodes, essentially our surface area of the risk or of the threat is increasing exponentially as well. All these nodes, like all these cameras or like robots or all the sources of which are generating data, they are connected over a network, and if they are not connected securely, then basically there can be intrusions and threats over that network. So it is crucial to keep the network secure. All the communication like SSH or RPC should be done through the secured communication, and we should certainly in our design consider avoid throttling and denial of service attacks by implementing thresholds for requests, etc. With that kind of concludes my talk. In just last slide, there are some fallacies to be avoided while designing the distributed systems. For example, network is reliable, latency is 0, bandwidth is infinite, network is secure, topology doesn't change. All these are fallacies and should be avoided when designing the distributed systems. With that, thanks for patiently listening to me, and I'm open to questions.